particular slide, where we said that if the stiffness matrices are calculated properly, by which we mean in an asymptotically correct manner, even the basic model for the closed cross-section, which is this 4x4 model, will take into account all kinds of deformation, including warping and the transverse shear, and therefore it will be as close to the 3D analysis as you want. But no 1D transverse shear variables and separate 1D warping variables, and therefore it will be okay for static or low frequency dynamics. But when you want to go for a high frequency dynamics, basically where the wavelengths are much shorter, then it is preferable to go into the 6x6, primarily to extract the information, additional information that you want specifically in terms of the transverse shearing rotations. So then we also saw that in the special case of thin-walled open cross-section beams, there is a large warping due to the torsion, primarily because their torsional stiffnesses are extremely low. And because of that, in addition to the contribution to the energy of the twist per unit length itself, there is also a contribution from the rate of change of the twist per unit length, which is kappa 1 prime, and its energies are fairly substantial to be included upfront itself. So this is sometimes called basically as restrained warping, something to deal with the boundary conditions in particular. So with this, we'll have one more concluding slide on this particular thing before regarding the kappa 1 prime, before we venture into non-linearities in the cross section, by which we either mean that these coefficients that you have, namely the S bars or S hat, will be either functions of the one-dimensional strains, or you can retain this in a constant form and add some more terms to this, which are basically non-quadratic, which basically contribute to the non-linearity as far as the dependence of the derivatives of this 1D strain energy with respect to this. So in the case where all of these are constants, very easy to see because it is quadratic. If you take the partial derivative of u, because it is quadratic in the 1D strains. If you take a derivative, the first partial derivative with respect to any one of these, then you basically get the corresponding one-dimensional equivalent force or equivalent stress resultant, as we call it. So that you see would be then linear in the 1D strains. But either if these are functions of the 1D strains, or if you have additional terms which are not quadratic, there could be higher powers, for example, then you basically have the stress resultants as functions of basically the 1D strains in a non-linear manner. So that's where the cross-sectional non-linearities basically come into picture.
So,
yeah.
So can it be somewhere 8x8 also? Somewhere we need in play to...
What do you mean by 8x8? Which additional terms are you thinking of? So let's say with this 6x6 you are basically thinking of adding 2 more, or which 8 are you referring to?
So warping derivative in thickness direction, like for plate W3 dash.
No, see,
gamma T.
Yeah, see, basically those are higher order terms. What we are right now looking at is basically something just next to the 0th order approximation, the classical approximation. This of course directly is the classical approximation itself, but if these are calculated in a proper way, it could even be the first order approximation also in some cases. But if you are going for even higher order approximations like second order or third order, then you will bring in the derivatives of the warping with respect to the larger dimensions. So in the case of the beam, it will be with W primes basically that we are looking at. But in the so what that will in turn bring is, because we are going to solve for W's in terms of these 1D variables, it brings in W derivatives with respect to x1, means the derivatives of these with respect to x1. And in fact, that is the way this actually appears. If you actually look at the derivation of this particular model, the reason why this kappa 1 prime comes is because of the derivative of a particular warping measure with respect to x1. And because that warping measure in turn depends upon kappa 1, therefore you have a kappa 1 prime which is basically coming out of that. So in fact, this is an example of what you're basically saying. So everything, whatever it is there, it will basically come in terms of in terms of that. So probably in some situation where, let's say, the bending stiffness is very low in one particular direction, for example in the case of a strip, when you go to a higher order approximation, not even first but maybe second or third, it is possible that you might get kappa 2 prime or kappa 3 prime, but the source of that is basically the warping derivative with respect to x1. In the case of plate or shell, what you have is you could have derivatives of w's with respect to x1 and x2. Okay, so those can come into picture in the 2D model that you have for the reference surface of the plate or shell. Okay, just to expand upon that last model that we had, where we not only had the typical 4x4, but in addition we had a row and column corresponding to kappa 1 prime. One very well-known example, at least in the structures community, in particular aerospace structures community, because we deal with a lot of thin-walled structures, in particular open sections like the I sections. So in such cases, there is the I section, for example, there is a problem related to the so-called bi moment, where you apply on the edges of each of the flanges. You have two flanges for an I section, so at each of these flanges you apply axial forces. One will be tensile, the other will be compressive. Again, it will be reversed in the bottom flange. When you have something like that, the resultant force is zero, the resultant moment is also zero, but you would still see the effect of that permeating through the I section. And that is a classical example because of the dependence of the energies, that is the one-dimensional energy of the beam on kappa 1 prime, that kind of an effect comes. If you were to ignore the dependence of the energy on kappa 1 prime, you will not be able to extract that kind of an effect. Another important distinction is therefore between the so-called interior warping and restrained warping. Whereas the effects like kappa 1 prime term have here is an example of restrained warping. The other thing that we have been talking about warping in general before is the internal warping, which is basically something which is all permeating, and it is something which is present in all kinds of beams. So that interior warping we would have solved with respect to the gamma 1, kappa 1, kappa 2, kappa 3 when we solve for the partial differential equations in the case of beams, or ordinary differential equations in the case of plates or shells for the warping measures with respect to the smaller dimensions, in the case of the plate with respect to the thickness coordinate, and in the case of the beam with respect to the cross-sectional coordinates x2 and x3. So now, since we have solved for those interior warpings, so basically what happens is that we resubstitute back into the energy, first into the strains and 3D strains, and then into the energy, and therefore everything gets expressed in terms of the 1D strain. So no longer the warping appears explicitly, because we have solved for the warping in terms of the 1D variables. It's the 1D variables alone which appear in the energy after the solution to the warping. So that's where the interior warping comes into picture. On the other hand, the restrained warping is something which is associated with the kind of boundary conditions that you have and how that permeates into the rest of the structure, primarily because your St. Venant's principle no longer holds good. What St. Venant's principle basically says is that as long as you are into the interiors, which means basically of the order of the cross-sectional dimension, if you go into the length of the beam, beyond that, it really doesn't matter how you apply the loads at the end. It is the resultants of those loads which actually affect in the interiors. But in reality, what happens is, because of this restrained warping, you can have the effects permeating much further inside as well. And that's an example of that is what we saw in the previous slide in terms of kappa 1 prime.
So I cannot visualize what is restrained warping. Here what is happening is the cross section is coming out of the, I mean, suppose this is it is coming out, that's one. But what is happening here is it looks like torsion, this one.
No, these are not like two examples of interior and restrained warping. This is basically what happens with respect to the I section in terms of warping itself. See, warping is basically defined as the motion of the particles over and above the average motions of the cross section itself. So that's basically warping. Now the source of that, what is actually forcing that to come into picture, into it being non-zero, is basically the 1D measures. Okay, if it happens to be the not just the 1D measures but their derivatives like kappa 1 prime, then it's basically a restrained warping contribution, something which has to deal with basically how the boundary conditions for the beam itself are. For example, if you have a fixed end, the fixed end could mean just that the 1D variables are 0, that is basically the displacements and rotations are basically 0 at that fixed end. Or it could in addition mean, depending upon exactly how physically you are applying that fixed condition, it could also mean that all the material points on that cross section are not allowed to move as well. Apart from the average motion, so even individual points are not allowed to move. So that's basically restrained warping. On the other hand, free warping is basically when you allow those end points to move as they are. Of course, the obvious case of free warping is at the free end of a cantilever beam. So there all points are free to move the way they want. So that's basically what we are referring to. But in reality, both can be combined into the same definition of warping. It's basically in terms of the source, where it is actually coming from, that we are basically looking at. One is basically coming from the so-called 1D strains itself, the extension, the torsion per unit length, and also the bending curvatures. But the other, which is the restrained warping, is basically coming from higher derivatives of those 1D variables itself. And because they are coming from the higher derivatives, it's basically the boundary the way actually it is basically contributing to that. Okay. So interior or Saint-Venant warping, we saw three models in the previous slide. One is basically associated with a 4x4 stiffness matrix. The other is a 6x6 stiffness matrix, including the transverse shear strains in addition. And then 5x5 stiffness matrix, where in addition to the classical, we have basically the kappa 1 prime rho 1 column. So now the interior or Saint-Venant warping will affect all three of them. The reason is that we are basically minimizing the total energy functional. We are solving for the warpings. The warpings get solved in terms of those 1D variables, and then we substitute back the warpings into the 3D strains, and then the 3D strains back into the 3D strain energy density, and then we can integrate over the cross section. So when we are doing that, basically what happens is that the warping gets indirectly in terms of the 1D strains itself. So the effect of that all enters into the stiffness matrix because of the integration that we do. So it is self-contained within this, the effect of warping. That's why you don't see explicitly the warping, even though we have taken it into account. You don't see in those 1D models that we saw on the previous slide any W's in any one of those three equations. So basically the W has somehow got into the information from W has got into the stiffness matrices. On the other hand, the restrained warping is present only in this particular last row and column here through the effect of kappa 1 prime, and because it is coming explicitly here in terms of a specific variable, though of course it's not explicit in terms of a W, but still it is different from what you typically have classically, and so that's basically the contribution which is coming in. And you see that in other words, there is an additional variable which is required over and above the 4x4 classical measures. And because it is appearing in the 1D strain energy density, this is what will be used in the reference curve analysis. Remember that our beam analysis is broken up into two parts. One is the cross-section analysis, the result of which is this, and then next you have to do the 1D analysis of the reference curve. At each location of that reference curve, you have to give the stiffness as calculated from this particular matrix. Now you see that because of the explicit appearance of kappa 1 prime, your 1D analysis is going to get affected, because it is this strain energy that we are going to feed into the 1D analysis. Whereas the interior warping is already contained into this, and therefore it does not explicitly appear when you do a 1D analysis. So this distinction is very important to observe, and of course this will come into prominence, as we mentioned already, only for thin-walled open cross sections where the torsional stiffnesses are fairly small. In all other situations, the warping information has already gone into this, and the 1D analysis is not affected by your warping in a direct manner.
So yeah. Roughly how much far we can say, like say Saint-Venant will say almost equal to the section width. If you take equal to, leave that, other is okay.
Right.
That is centimeter will say 200 mm per section, 200. By using this restraint warping, how much distance we can say we are not going?
Saint Bernard's principle completely fails.
Oh.
So this kappa 1 prime is something which is going to permeate throughout your beam. So it's not limited to any particular region, or it's not saying that it's very large at that region and it is decreasing in size over thing, because this is something which is going to permeate throughout your beam, and so that that's the primary difference. Whereas all other effects can decay and die down. This will not. So next we go on to cross-section and nonlinearity. In all the previous slides, whatever we have seen, whether it is the S-bar matrix or the S matrix, the 6x6, or the 5x5 S-hat matrix, in all of those situations, in the simplest case, you will have basically all of those elements being constants. Now what is the situation, or are there situations where you can have those as not being constants, or the fact that we might have to add non-quadratic terms to the energy, which are just two equivalent mathematical ways of dealing with the same thing. So that's basically what we are going to look at in the rest of today's class. So as I said, cross-section analysis are typically linear. In other words, your S matrix or S-bar matrix or S-hat matrix are consisting of constant terms. But there are indeed exceptions, and some of these are very important exceptions because they are very practical situations, especially in aerospace applications. And that's some of those we will basically look at. The first example is the so-called Brazier effect. And this is named after a person, Brazier, who first modeled this. So his name is Brazier, and that's why it's called the Brazier effect. But physically what it means is there is a nonlinear bending of thin-walled closed cross-section beams. So any closed cross-section beam that you take, if you basically try to bend it, it will bend in such a way that it is difficult to bend it in the beginning, and then it becomes much easier to bend it as you go. It's a very simple example is if you take a garden hose pipe, for example, you would see that basically if you try to bend it, initially it is a little more difficult, but once you have achieved some level of curvature, it becomes much easier. And even more drastic example would be a drinking straw, a plastic drinking straw that you take. If you try to bend it, you see very soon there will be a kink which is formed. In other words, it bends in such a way that in the location where the curvature is fairly large, you would see that it no longer is a circular cross section. That thin-walled circular cross section that it had now basically flattens out. Okay, so that flattening, what it does eventually is basically to reduce your bending stiffness. So initially you have a circular cross section, you try to bend it, it starts ovalizing in such a way that your bending stiffness slowly starts decreasing up to a point where there's a drastic decrease or drop in the bending stiffness, and basically that's where the so-called instability occurs. It's a local instability phenomenon. So that if you don't have a nonlinear model, you will not be able to extract this. You would assume that the cross section always remains circular, the stiffness, bending stiffness remains the same, and you will not be able to extract this kind of behavior. So you have many shafts, for example, in many applications which are the thin-walled circular shafts, and if they are subjected to bending loads, then this, for example, will become critical. So it's not necessarily circular cross-section. Any closed cross-section, as long as it is thin-walled, will behave in this particular manner. Even, for example, a box beam, which is typically a rough-cut model for, let's say, the interior of an aircraft wing, you can take the front spar web, the rear spar web, and the skin of the top of the wing and the bottom of this wing, basically to constitute the so-called box beam. It could be basically, of course, have stiffeners at the ends corresponding to the flanges of the spars, but nonetheless it is a closed cross-section involving thin walls, which include the top part, which is the skin of the upper surface of the wing, the bottom surface of the wing, which is also again the skin, and then you have the two spars, which are basically the webs of the spars, and those are also fairly thin structures. Now that is subjected to a bending load primarily because of the lift distribution in one direction and the drag distribution in the other direction, and these basically cause the bending of those. Of course, major part of the bending is resisted by the flanges, so it's only a small part of that which goes into this. But nonetheless, there is a bending, and that bending behavior cannot be accounted for properly unless you take these nonlinear effects into picture. So this is important in the study, for example, of composite top tubular beams used as trusses in space structures. If you've seen many of the space structures, they have truss-like structures, especially for the deployment of antenna and so on and so forth. You would see that truss-like structures, and many of those elements of the truss are basically thin-walled, either circular or non-circular cross sections, but basically closed cross sections. So it's important in the study of such composite tubular beams in space applications, antenna legs, submarine hulls, cooling tower shafts, risers in offshore structures. Once again, they are closed section, thin walled. Medical tubing, for example, it agrees with the kind of garden hose example that I was giving. So again, the stiffnesses are fairly low there, and therefore this effect is even more predominant in such situations. Fishing rods, ski poles, etc. Anywhere where you basically find closed cross sections with thin walls.
Sir, in aircraft wings, we consider now we have told only about the skin and the spot.
Yeah.
Now we have a rib also, so maybe this effect of thin wall might not come because of the ribs.
Yeah, see what the ribs basically do is, so your transverse stiffeners that are there will only restrict the length of your beam. Okay, so in other words, you can consider the region between two transverse shear stiffnesses as basically the beam. Okay, so what it makes is, it makes it a shorter beam, it makes it a stubbier beam basically. So making the transverse shear effects probably more important. Okay, but nonetheless, when you have low speed aircraft with very large aspect ratios, then you have fairly long wings, and because they're low speeds, the loads are fairly small, and you may not have as frequent transverse stiffener spacings. So in such situations, for example, it is very important. Okay, so but basic idea is that most of the bending is indeed taken by your longitudinal stringers as well as the spar flanges. Okay, so the spar flanges, for example, those will take most of the bending load, but still a part of the bending load does come into picture. Okay, so in that sense, of course, the brassiere effect is not that predominant compared, for example, with the next effect that we are going to talk about, but I'm just listing them as examples. And again, I will list only 2 examples, but that's again not comprehensive. There are many other kinds of nonlinearities as well. This is just something which we can kind of visualize that and basically see what is the physical source of this thing which is happening. So that's the primary reason from which we are coming. But nonetheless, you may not, of course, go to the extreme case where you're looking at a drinking straw, it's developing a kink, that kind of a limit moment instability. It would be too funny to say that something like that would happen here. I completely agree with you. But even in the initial stages, as you shall soon see, there can be some nonlinearity in the bending moment versus curvature relationship. In other words, your EI is not a constant, the bending stiffness is not a constant, and unless and until you take that, you cannot get an accurate estimation of the stresses and so on and so forth. So that is or even the deflection for that matter. So that is the reason why we are talking about it. Again, it also in this case it's because most of the bending loads are taken by the spar flanges, and further you have many stringers as well. Those are taking. So in situations where you have, let's say, a monocoque kind of construction, you don't have a semi-monocoque construction, again it will become very critical indeed.
So this thing will happen only in one beam reference line analysis. Why we are studying this thing in cross-section analysis?
See, basically, what does the cross-section do? Cross-section analysis, one of the main results which it gives is the relationship between the stress resultants at a cross-section and the 1D strains, right? So one of them is the bending stiffness, okay, which relates, let's say, M2 with kappa 2 or M3 with kappa 3. It's basically in a 4x4 matrix that we are talking about here. 4x4 matrix again into the same 1D strains. Now if you look at the 3-3 element here, S33 bar and S44 bar, so those are basically your bending stiffness, right? So now what is basically happening to this bending stiffness when you have a circular tube? Let's say you have a circular tube like this, which is thin walled. So you take any particular cross section, you are applying of course a bending moment on this, on both the sides. Okay, so now this is basically bending. So when it is bending, if you look at this particular cross section, let's say this is x2 direction, this is the x3 direction, x1 being along the length of the shaft. And basically if you look at the cross section, what is basically happening is that it is basically changing into something like this. It is flattening. Okay, the extreme of course is when it forms a king, but basically this is what is happening. So now the bending stiffness that you're interested in relating is this bending moment with the curvature that this basically gets, right? So in other words, it's a relationship between your kappa 2 bar or kappa 3 bar, whichever direction that is in this case. Of course, the bending moment is about x2, so it's kappa 2 that you're looking at. So it's a relationship between kappa 2 bar and your M2, which is in turn defined as the partial derivative of your one-dimensional strain energy density with respect to kappa 2 bar. So this is your bending moment. Okay. So if you are not taking this into account, you would have just got, for example, in the case of isotropic beam, you would have just got this to be EI2. This is your bending stiffness, right? But if you see, the geometry is changing, and the geometry information basically goes into this, and so it means that when this is basically flattening out, your I2, which is about this x2 axis, the moment of inertia, is going to reduce, right? Because your moment of inertia I2 is defined as your x3 squared dA integrated over that cross-sectional area, whatever that thin wall cross-section is. Now your x3 values are reducing for the same material points. The material point which was over here has now come to here. In other words, its x3 values have reduced. So when you integrate your x3 squared dA over the entire cross-sectional area, whatever this is, it's going to be much lesser now. So in other words, your bending stiffness is going to be lesser. Where is that effect observed? It is in the cross-section analysis. That's why the cross-section analysis is getting affected. Okay, so it's basically these terms are going to get affected. But how does it actually come into picture? It's because of warping. See, what is happening is now it is no longer a rigid body-like motion that is taking place. Of course, there is a rigid body-like motion because of this basically curving up a cross-section over here would probably go over there. It is rotating, right? But other than that rigid body-like rotation, there is also warping which is taking place. Not out of plane warping, but you basically have an in-plane warping over here. Okay? So in other words, a point which was here has now moved to here. Now that measure is basically your W2. So your warping W2. A point which was here has basically come here. So that is basically your W3. Okay. So of course W2 and W3 are functions of x2 and x3. So they're going to have different values at different locations. Now this W2 and W3 being non-zero has caused this S33 and S44, or in other words your EI2 or EI3 to basically reduce. Okay. So because we have substituted these warpings into the energy, they are in terms of your kappa 2 and kappa 3, and when we integrate that over the cross section, that basically says that as W2 or W3 are non-zero, that's going to basically change your S33 bar, S44 bar. In this particular case, because of the way this W3 is, it primarily reduces the moment of inertia about this, and in turn basically reduces the bending stiffness. So this is of course in the case of an isotropic beam. Even in the case of a composite beam, something similar happens, and basically your stiffness here reduces. So the effect is primarily in the cross-section analysis. Okay. And then of course you are going to substitute this in the 1D analysis, therefore the 1D analysis also gets affected. Okay, so this is one example. This is the brazier effect. The other very well known example and practically much more important for aerospace structures, in particular helicopter rotor blades, is the so-called trapeze effect. Now you see I use a small t here because trapeze is not the name of a person, unlike brazier. So therefore you use a small t here. Trapeze is basically an artist in a circus who basically, if you have seen some kind of a circus, you see that there are two ropes, and then there is a rod which is attached to those two ropes at the ends, and then basically this person swings from that and turns around as well. Now what is basically happening is that you increase or decrease the tension in these springs by basically moving your body weight around, and at the same time when you're turning, you're basically inducing some twist. Now this extension and twist are basically coupled, and that phenomenon is what is known as the... So now there are some subtle differences between these. Both are cross-sectional nonlinearity examples. In this case, it is a diagonal element which is getting affected, either S33 or S44, that is your brazier effect. But here it is an extension twist coupling that we are basically looking at. In particular, you are looking at this term S12, which basically couples your gamma 11 bar with your kappa 1 bar. So that's basically your S12 that we are basically looking at. First of all, it is an off-diagonal term. Secondly, this is something which is more commonly observed, or it just comes into prominence in open cross-section beams, unlike here which is closed cross-section beams, but both are thin-walled. Okay, so unless and until it is thin-walled, your warpings are not large enough. If you have a solid cross-section or very thick-walled closed or open cross-sections, the warpings are not significant, and therefore the in-plane warping in particular is not much, and therefore the change in stiffness is not much. So there are some similarities between these. There are also some differences between these. So, but the primary thing that we are concerned about here is the fact that in the cross-section analysis there is a nonlinearity, or in other words, your stiffness matrix is something which is not made of constants, but it is going to be a function of the 1D variables. But again, as I said, mathematically speaking, that can be put in a different way by instead of saying these are functions, you just add some terms which are non-quadratic as well. So that's another equivalent way of putting the same thing. But the end effect is that whatever your stress resultants are going to be, they are going to be not linear functions of your 1D variables, but non-linear functions of your 1D variables. And that enters as an input into your 1D analysis of the reference curve, and that's where you will see the large differences, whether you consider these nonlinearities or you don't consider these nonlinearities in terms of their agreement with 3D analysis, or for that matter what is observed in reality. So this is critical in analyzing rotating structures. I gave you the example of helicopter rotor blades, once again propellers, turbo machinery blades. Why is it so important in these specific examples is the fact that these are rotating structures, and rotation induces the centrifugal forces, and which to a structural engineer is nothing but an axial load, an axial tensile load which is occurring on these blades. So as this helicopter rotor blade is basically rotating at a particular speed, it basically gets pulled out, which is basically a tensile load on a beam which is rotating. So that's that tensile load basically occurs in this extension that we are talking about. And twist is a very important feature in all of these rotating structures, in particular in helicopter rotors. Almost all of the control which happens of a helicopter is through the change of the twist of these blades. Of course, there is an initial twist in most of today's rotor blade designs, but in addition, the way the pilot operates the helicopter, that is whether he wants to move forward or rearward, sideways or upwards, he basically has two pitch sticks that he controls. One is called the collective pitch stick, which is basically either lifted up or brought down, and then there is a cyclic pitch stick which can be moved either left, right, front, back, or combinations of these in any direction. What actually happens to the helicopter when the pilot does these things is quite intuitive. In other words, if he lifts this, you get more lift power, and basically the helicopter gets more thrust upward direction. It basically can move up in a climb up basically. if he moves down, you basically come down. On the other hand, moving forward, basically what it does is it basically changes the rotor plane from being horizontal to tilting forward, so that the resultant force which is coming because of the lift acting on the blades is always perpendicular to this rotor plane, and instead of being vertical, that force now has a component which is horizontal as well, and therefore in addition to maintaining the balancing the weight of the helicopter, it also starts moving forward because of the forward component of the force. But this is as far as what actually happens to the helicopter. But the way the engineer actually has devised this to happen is much more complex, and this all happens because of the twist, and that's why the twist extension coupling is very important. Extension you've already seen, there is a centrifugal force, there is extension. Now the twist comes into play because first of all there is an initial twist, as I said. In addition, these blades, the angle of attack can be changed, and what actually happens when the pilot is operating these sticks is the change of these angles. For example, the simplest situation is the collective pitch. So when you basically increase or decrease the collective pitch, all that you're doing is you're simultaneously changing the angles of attack of all the blades. So basically what happens is all the angles of attack change, and therefore basically the helicopter rotor plane now starts coning, and basically it has an increased lift force, and that's basically what makes it to climb up or down. On the other hand, when the pilot is, let's say, moving the helicopter the cyclic pitch forward, the rotor plane has to tilt forward. The way that happens is because of the flapping motion of the helicopter rotor blades. As the helicopter rotor blade goes around the azimuth, it also has a flapping motion that is happening, and this flapping motion has to be such that it is periodic, and at this location it has the minimum flapping, and at this location it has the maximum flapping. So for the helicopter what happens is, and at these two locations it's somewhere in between. So basically the end effect is that the rotor plane seems to have tilted like this, but what is actually happening in terms of the beam is it's actually bending. It is bending down here and it is bending up here, and it's somewhere in between here, and it is cyclically undergoing through that particular loading of bending. Bending is basically varying in a sinusoidal or cosine of different harmonics, the primary being same as the RPM of the rotor itself. Now, where does the twist come? Because what I told is just the bending, but aerodynamically speaking, what happens is that the bending and the twist are coupled. In other words, it is the change in the angle of attack which changes the lift distribution on the thing, and therefore there is a coupling between the lift and the twist. So, and the lift in terms of a structural engineer that we are primarily concerned with is it causes bending. Okay. So now what is basically happening is that you are changing the pitch here to the maximum value or minimum value rather. So you are changing the pitch angle, that is basically you are twisting this to the minimum value, so that at this particular location it has the minimum flapping. In other words, aerodynamically speaking, the twist and the bending are coupled to each other, but they have a 90-degree phase lag. Okay, so if I make the pitch minimum here, I get the minimum bending over here. Similarly, at this particular location, when the helicopter rotor blade comes here, if I increase the angle of attack to the maximum, what basically happens is at this location I have the maximum upwards bending. So that's basically what happens, and eventually you have this. So in other words, you have a pre-twist, you also have this pilot controlling both these sticks. Again, the similar kind of thing happens with the left-right motion as well. But the whole idea is that almost all of the controls of the pilot, except of course the rudder, which is controlling the tail rotor, once again by similar fashion. But as far as the main rotor is concerned, all of the control actually happens through twisting the blade, and you already have the centrifugal force causing the extension. So this particular coupling that is there becomes extremely significant, and it's the same with propeller blades as well.
Sir, this brazier effect is mostly predominant for close cross section.
Yeah.
Say we compare a thin walled completely rectangular cross section and a thin walled C section.
Mm-hmm.
You bend it.
Yeah.
In the sense, I I can't imagine, because this thin walled rectangular cross section has material. The material provides some stiffness to this non-linear bending in all the sides. While in C section, one side it's free, so it's much more easier to bend. So this brazier effect should be predominant in open cross sections also.
It is present there as well, but it is something which has been studied more predominantly in this. See, I'm just giving these as two examples of nonlinearities which occur. What you're saying is perfectly true, that you will have brazier effect even, for example, in a channel section, but the trapeze effect, which will be much more dominant compared to the brazier effect. In fact, even if you take a thin rectangular strip, you would find both these effects. In other words, a thin rectangular strip, you can not call it either as an open section or a closed cross section or a solid cross section. It's somewhere, it's a hazy kind of a thing in between all of these. So it has the effects of all of these things. It will have all of these. And again, as I said, these are not the only two cross-sectional nonlinearities. You will have additional cross-sectional nonlinearities as well. So it is possible that you can have sometimes a little bit of trapeze effect even in the closed cross-section, but because the torsional stiffnesses are large, the effects will not be as much observed as in this particular case. But the brazier effect, on the other hand, what you're saying is perfectly true, that whether it is open or a closed cross-section, the in-plane warping can be such that the moment of inertia changes quite a lot, and you can have a very large thing. So the reason why we specifically mentioned closed cross-section is there are very practical examples where this particular effect has been observed and has been taken into account in the modeling. If it were not, then it would have caused issues. Whereas in the case of open cross-section beams, all of those nonlinearities will have to be taken into account simultaneously.
Well, is it also because of we have centroidal axis and the shear center which is off in the open sections, so the torsion and also the bending effect come into the picture because of extension?
That is a separate effect. Okay, so that it is not that which is causing the cross-sectional nonlinearity to basically occur. The cross-sectional nonlinearity, the source is always the in-plane warping. Okay, so it's the in-plane warping which changes the shape of the cross-section and or the size of the cross-section, because of which you basically change all the stiffnesses, and that's the source of that. Whereas again, it is because of a geometric feature, that because of asymmetry, for example, you can have the shear center and the centroid separate from each other, and that can cause a different type of coupling. So most of that will basically be observed in the effects in having non-zero values for your off-diagonal elements over here. Okay, in particular, let's say the transverse shear and the bending will be coupled, the extension and the torsion will be coupled. There will be many such things. And again, there is also a way of handling that, because remember that we have freedom over the choice of the reference curve. So you can choose the reference curve according to the convenience. So depending upon where you choose the reference curve, either as the loci of the shear centers or as the loci of the centroid, you might be shifting this particular effect to different regions of the analysis. Your end results will not be affected, your 3D analysis, but your intermediate results, your cross-section analysis as well as the 1D reference analysis will all be affected in such a way that basically one compensates the other and your end result is going to be the same. Okay.
So in the sense, this brazier effect is predominant only in for close cross sections. This brazier effect is much more predominant than trapeze effect.
That's correct, yeah.
And similarly, in
Exactly.
open cross section, trapeze effect is much more than
Correct,
brazier.
precisely.
This is for separate case. In
Yeah.
case of we consider a wing,
Uh-huh.
in that if we consider the spars, they are kind of open cross section,
Uh-huh.
and the whole wing structure, skin structure, if you
Yeah.
consider it's close cross section,
Yeah.
then there is coupling between these two. Which
Yes. See, basically there are many different ways of analyzing an aircraft wing. Either you can treat the entire aircraft wing as a single beam with a particular loading, which is the equivalent loading coming from the aerodynamics and or the weight and all the other engine, etc. Or you can treat each one of these components separately. So you can treat the spar separately, you can treat the stringer separately, you can treat the skin and the box beams which come because of the spar webs and the skin, all those separately. So when you're doing that, of course you have to look at the interfacing weights which come because of that. When you're looking at it in a component wise like that, then you would see that the again it's also in terms of how the load gets distributed. So you know that most of the bending goes into the stringers and the spar flanges. The torsion basically goes into the webs and the skin. So now you're basically seeing that the primary effect of this particular torsion that you're having is basically into a closed cross section. So then you will not have that the trapeze effect problem to be very critical. On the other hand, the bending that is basically taking place is with respect to an open section. So there, of course, you will have the cross section basically changing because of the warping and the bending stiffness changing. The brazier effect will come into prominence. But what we are listing here are simplistic examples. We are not talking about a complicated structure like an aircraft wing where you have all those the skin and the stiffeners. But just consider just a circular tube alone all by itself without stiffeners. Just consider an open cross section alone. So such situations you can visualize better what is happening. But what you're saying is true that in the real situation it is a much more complex phenomena which is happening. But even there, if you break it up into components, we can actually observe these.
No, in the sense I wanted to know whether if you consider a combination like that, whether the brazier effect would be much more predominant or trapeze effect in that combination of open aircraft wing case. You can consider the whole wing with the skin and the spar.
Yeah. See, basically in an aircraft wing, they say the tensile loads are not much. Okay, so you would not have this extension twist coupling being a phenomenon to be of interest. It's more in rotating structures. That's why we gave the example of the helicopter rotor blade. Okay, so there the brazier effect would be more important.
Yeah, but so these effects will not look beforehand. These are
yes, that's correct.
We'll start with some, let's
say,
is telling the same problem.
Yeah, whatever I'm presenting is more from the motivation point of view. I'm saying, but it's not like I'm observing particular effect and then trying to capture it through the variational asymptotic method. No, these are all automatically captured when you apply the variational asymptotic method. We're just saying the practical relevance of many of these things before actually applying the VAM to extract these kinds of information in a mathematically rigorous way.
Means we'll do the cross-section analysis between two spars, between two ribs.
Okay.
One cross-section will take those properties, whatever two spars and whatever skin is there, full thickness, everything. Then we'll do the cross-section analysis.
That's correct.
We'll get the warpings and then S matrix.
That's right. Yeah.
Then only we'll see whether this thing is there.
Exactly. Yeah.
Depending on loads.
Exactly. See, the cross-section analysis is independent of the loads. So you are getting a general thing irrespective of what kinds of loads you might have. You might have extension, you might have torsion, you might have bending, whatever. So the cross-section analysis is independent of that. So your 1D analysis then will bring in the loading into picture, and then the loading, depending upon what kind of loading it is, some of the terms might be important, some of the terms might not be important. For example, this term is not important. For example, in the aircraft wing example where there is no centrifugal force, there is no not much of a tensile load which is happening. So then basically this S12, though it will be there in your cross-section analysis, it may not enter into your 1D analysis when you are doing the 1D analysis, because the kind of loads that you are having, those terms will drop off. And then only the remaining terms will be of further interest.
Roughly 6 by which metrics will go for this wing analysis?
A wing basically is like a closed cross section. Again, it depends on the class of aircraft also. But let's say if you're talking about let's say low aspect ratio, low speed aircraft, for example. So then you basically have predominantly the bending loads which are coming because of the lift distribution, bending load because of the drag distribution. Again, depending upon the location of your aerodynamic center, which is quarter chord, and then you have your lift and moment there, and there's also pitching moment depending upon whether you have camber or not. So all of those are basically the loads. So now your pitching moment along with the moment arm that the lift or drag might have with respect to your beam reference line can cause torsion as well. So that torsion will also be there. So it's a question of which of these loads are kind of dominant. So predominantly your lift distribution bending load will be dominant. So for example, your brazier effect can become critical, okay, especially if you have just a monocoque construction. But once you have a semi-monocoque construction, what happens is the bending load is now taken by the stringers and the spar flanges. So now when that basically happens, then your the skin is not taking too much of a bending, and therefore the change in cross-sectional shape of that will not be of much importance. But as Valiappan pointed out, you basically can have the brazier effect even in the open cross-sections. Okay, so your the open cross-sections can also change. But the way this moment is distributed here is such that you have axial loads, that is axial tensile and axial compressive loads. For example, when the wing is bending like this, the top portion is basically all the stringers on the top surface are basically undergoing compression, and on the bottom surface they are undergoing tension. So it's not actually a bending which is happening. So they are just tensile loads which are basically happening. Now if there is a combination of that tensile and some torsion which is also there, then this kind of an effect can come into picture. So it all depends on a case-by-case thing, and also the relative magnitudes of these various loads, the geometry, the material properties, all of these come into significance. So that's why we develop a very general theory, and then we basically say that depending upon the class of the beam cross-section, which we'll come to in the next class, so then we basically decide which particular model is appropriate for that. Again, it's not a question of us deciding, but basically based on the small parameters, it is automatically decided. It's just that we take that into account.
So this cross-section analysis is common for any cross-section you take in a particular beam?
The procedure is common, but the results will be very different for different cases. For example, we already showed in the first slide that we saw today 3 different cross-sectional models. One is a 4x4, the other is a 6x6, and the other is a 5x5. Now, which one to use is not something that I decide just based on my whims and fancies. It is basically for a certain types of cross sections, one is more relevant compared to the other, and that the WAM will tell you. When you apply the WAM, it comes out obviously that one is more important than the other, and that end result is what I said. For example, when the 5x5 case where you have kappa 1 prime is important only in open cross sections. It's not important in closed cross sections, because in closed cross sections the torsional stiffness is very large, and therefore the torsional curvatures are very small, and therefore the change of curvature along the length is also very small, and therefore the contribution to the energy of a kappa 1 prime squared is very, very small compared to the contribution of kappa 1 squared itself. So therefore that effect becomes unimportant. And again, it's not something that I decide, it is the mathematics of the procedure which decides that. So in terms of the overall procedure, it's going to be the same irrespective of what beam you are going to talk about. But the end result in terms of the cross-sectional analysis, what stiffness matrix it gives, will depend upon what kind of cross-section it is.
In case if in a beam we apply a moment, any cross-section which we analyze, the moment will be the same. So that kind of it's okay.
If it's a pure bending moment.
Pure bending.
Right.
In case if it's a point load at some point, that will there be any difference when we analyze a cross section at point where load is not applied, and there is only moment due to this load, and that cross section at which the load is applied? Will there be a difference between these two cross section analysis?
One thing of course is your the bending moment is varying along the length. That's something which will be taken care of by your 1D analysis. It's not something which is going to affect your cross-sectional analysis unless and until your cross-sectional shape itself changes along the length. For example, a tapered beam. Most aircraft wings are basically having a taper with a smaller chord at the tip compared to the root. So basically in such a situation, you'll have to have different cross-sectional analysis at different locations. But it is not because of the difference in the loading value. It is more because of the change in the cross-sectional geometry and or material distribution.
But in the sense when you, at a point when you apply, at a cross-section when you apply the load, you expect that cross-section to distort a bit much more than the others.
See, typically the way the aircraft wing is designed is such that where you have concentrated loads, you will typically have a transverse stiffener, a rib. In the case of the fuselage, you'll have bulkheads. So for example, where the wing is attached to the aircraft fuselage, you will have bulkheads there. So that concentrated load, whatever you are applying through the wings, gets dissipated through the bulkhead into the length of the fuselage. So that way there is a effective transfer of loads, which is basically taking. Again, in the wing where the engine is attached, you will find transverse stiffness, the ribs. So basically, again, the weight of the engine as well as the thrust load, which is coming because of that, will get diffused into the structure. Okay, but otherwise, if it is a concentrated load, then there can be a lot of local effects which are taking place, and those are entirely three-dimensional. Yeah? Any beam theory, even asymptotically correct beam theory, will not be able to handle something like that. So in such situations, what you have to do is you have to do a 1D analysis for the entire thing, and in that local region where the concentrated loads are there, you might have to do a local 3D analysis, using the results of your 1D analysis for the rest of the things to give the boundary conditions for that. You can do a local 3D analysis for those regions. But usually the case doesn't occur because of this diffusion through the stiffeners.
Same thing, sir. Yeah. Actually, this thing is very prominent. This wide load during the beam in beam length. We'll do the process analysis. That's okay.
Yeah.
Then 1D analysis will do using those properties, those as sections throughout beam. For particular point load, we can only do 3D analysis.
Just around that point load, what is happening to find out, you have to do a 3D analysis.
That's what we are 3D relations we are getting. In our IM itself, we are getting 3D relations. This will give?
No. So those 3D results will not be very accurate in those locations where the concentrated loads are there. So in the vicinity of that, you will have fairly accurate thing, but very close or at the point of application of the concentrated load itself, you will not get proper results. So that's why that region you can do a local analysis. For example, the location where you're talking about landing gear is attached to the wing. So at that location, you can do a analysis for the entire beam using in the 1D analysis as inputs the load which is coming from the landing gear. You will get overall results. You can even recover the 3D results. 3D results will be very accurate, stresses, strains and deformation almost everywhere except at the point of application of the load. So around that location you can take a small area, and for that location you can do a 3D analysis giving the boundary conditions from the results of your 1D analysis, beam analysis, and then you basically of course after recovering the 3D results. So then you can apply that as the boundary conditions, and then you can get the exact stress distributions and or deformation patterns in that location.
Okay, localized,
yeah,
no problem. But means loads will go in point loads also will go in 1D analysis.
Exactly, yeah.
Even point load also will go in 1D analysis as a function of x1.
That's correct. So loads don't affect the cross-section analysis at all. They indirectly affect through the gamma 1, kappa 1, kappa 2, kappa 3 because in the nonlinear case especially because your S's are going to depend on them. Okay, so indirectly it will be affecting, but the actual way of applying the loads does not come into picture. It is the effect of that. See, it is the extension which is causing this. It is the bending which is causing bending loads which are causing this, including the loads that you are talking about. The landing gear load is eventually going to cause the bending of the wing, right? If the landing gear is on the wing, basically it's going to cause a bending of the wing. So if some of these matrix elements depend on your, in this case, let's say along the chord you have x2 direction, so you're basically creating a M2 kind of a bending. Now that M2 kind of a bending is basically going to be related to this kappa 2, and if this is a nonlinear thing, then your S33 can depend on kappa 2. So there is an indirect way in which it is contained in the cross-section analysis, but not explicitly. You're not taking the loads into picture there. The curvature created by the load, that comes into picture in terms of the cross-section analysis. So you don't need to bother about it at all. Okay? It purely comes in terms of these 1D variables. It's only in the 1D analysis that you apply those loads appropriately at the locations at which they are occurring. Okay, let's talk a little more detail about each one of these effects that I just described in the previous slide. Start with the Bezier effect. As I said, it's a nonlinear relationship between the bending moment and the bending curvature. So for example, if you draw a curve between the bending moment on the vertical axis and the curvature on the horizontal axis, then basically bending moment is in Newton meters and your curvature is in per meter. And then you basically see that if you have a linear model, that is basically your bending moment is related to kappa 2 bar. So basically your bending moment is related to kappa 2 bar through this constant of proportionality EI2. So basically you if EI2 are not changing, that is you don't take this nonlinearity into account, you should have a straight line with a slope equal to EI2. So that's basically what you would have as a slope over here or slope over here depending upon different materials. So these are all for composite structures. So for example, you have unidirectional 0 degree plies around just 8 plies. Then you have different types of other layups, 45 minus 45 0 or 0 plus 45 minus 45 for the same composite material, same volume fraction, same fiber and same matrix. So depending upon the actual layup, you will have different stiffnesses which are there initially. But then as you increase the bending load, it will be almost linear up to a certain extent, and then it basically bends downwards. In other words, your curvature increases much more rapidly. Okay, so the slope of this is your EI2. So what is happening as you come here is your EI2 is reducing because of this flattening which is happening, because of which your I2 is basically reducing. So when your I2 reduces, your EI2 reduces, and that's basically what is happening. But the way the variation asymptotic method tracks this out is through your in-plane warping, by which we mean W2 and W3 components. So that's basically what is resulting in something like this. And if you actually see, if it is nothing else happens, like for example the material failure doesn't happen or local buckling phenomena doesn't happen, etc., which can be the situation depending upon the geometry and the material itself. In such situations, it will reach a peak and then it will actually fall down as well. So that's something which can happen as well. In other words, there is a limit moment instability. Okay, so that's basically happening there. In other words, after a certain value of moment, even without increasing the value of the moment or the value of your bending loads, you're basically seeing a rapid change in curvature. And that's the example of the drinking straw that we are talking about. As soon as you, or there might be local buckling which is taking place. Remember that bending is resisted by tension and compression. So if I'm applying a pure bending like this, the top surface is under compression, right? So the top material elements will all be under compression. So there can be phenomena of local buckling also taking place. There will be kinks which will be formed over there. So that can also occur sometimes before. That is not this limit moment instability. These are two different things.
Yeah, actually I have one doubt.
Yeah.
How do you differentiate between local buckling and this kink formation?
See, the local buckling is a global phenomenon in the sense that it is a 1D phenomena. Okay, so it's basically a relationship between your bending moment and curvature, assuming that none of these local problems happen. See, even material failure is a local problem. It starts off at a particular location where the stress is so severe that basically the material at that location fails, and then of course it spreads, the damage can grow. But basically it's a local phenomenon. Similarly, your local instability is because of a particular location where the compressive stresses are large and the geometry is such that, because it's thin wall, remember, it can have a local kink which is taking place. Whereas the kink that I was talking about earlier is a kink in the entire structure. See, in a drinking straw, it's not a local phenomena which is happening when you bend it beyond a particular point. It's a kink which basically forms. But in engineering structures, unlike in a drinking straw, that is not what happens first in most cases. It is the material failure and or the local buckling which happens prior to the overall global 1D instability. Yeah, so basically you see these exaggerated situations where you basically see what is happening, and also you see the stress becomes fairly large at those locations. So now let's look at that, part of which I've already talked about, but in a more formal sense. So basically you have a circular tube. The way you deal with this problem is you first introduce the coordinates x1 along the length of this shaft, x2 and x3 as cross-sectional coordinates. And because you can take advantage of the axis symmetry, so you can introduce even another Cartesian coordinate system where you have a tangential direction and then you have a radial direction, basically circumferential and tangent and radial. So then if you express in terms of that and the theta at some location, let's say theta is 0, and then you basically talk about theta varying from 0 to 360 degrees. If you express in this set of coordinates, typically the derivation becomes much simpler, taking advantage of the axis symmetry in the geometry. Of course, the loading itself is a bending load, which is not axis symmetric loading. So the advantage is not throughout the derivation, but at least parts of the derivation get simpler if you use a coordinate system basically like this. So when you do that, first, so you introduce that, then you define the so-called 3D strains from the kinematics and bring the 1D kinematics into picture, the relationship between the 3D strains and the 1D strains. And then you substitute those 3D strains into the 3D constitutive law, which is basically the energy per unit volume of the structure, this particular structure. And then you integrate that over the entire volume and you minimize with respect to the warping measures. Then you get differential equations with respect to the warping. And then you solve those differential equations along with the associated boundary conditions and so-called global constraints, because you have to remove the rigid body translations and rotations which are already accounted for. They should not occur again in the warping. So once you do all that, you solve for the warping, you substitute back the warping into the 3D strains. Again, you integrate the energy, 3D energy density in the cross-sectional area, then you get the energy per unit length. So once you do that, you basically end up with a equation like this, which is basically the 1D energy per unit length of the beam in terms of the 1D strains, and then you have a stiffness matrix. In that you can specifically look at this particular element, S33 element, which is the bending stiffness relating kappa 2 bar to M2, which is the bending moment about the X2 direction. So when you do that, that is, of course, in a isotropic beam it is EI2, but it's much more complex, not overly complex, but more complex than this in the case of a composite tube. So, and again, depending upon the layup and the material properties, that can change. So the whole idea is this: so you apply a particular bending load that causes a bending moment, which is a stress resultant in the sense of the beam. So then you have that bending moment M2, which is about the X2 direction. So at zero load, it remains a thin-walled circular cross-section. As you have small curvatures, you have a little bit of flattening, hardly any change in the bending stiffness, and that's basically what you see. It's almost a straight line in these areas. But then as you start increasing the curvature, what happens is, either this is an example of a local instability that I was talking about. So basically it's the portion in which there is compression, so small portions of that can undergo a kink. But if this were not to happen and material failure were also not to happen, then you would have a limit moment instability where you have this kind of a behavior. So you have a bending moment. The result of that is the curvature kappa 2. So that's M2 by EI2 in the case of a linear isotropic material. Then you have kappa 2 increasing. So you're going from small curvatures to larger curvatures. So when you do that, you end up with in-plane warping. This direction doesn't agree. So what I'm talking about is this is X2 and this is basically X3. So the flattening happens in the X3 direction because the moment that I'm applying is about the X2 direction. So because of that, this flattening basically happens, and the moment of inertia that I'm interested in calculating for your S33 component is the bending stiffness about the X2 direction is basically about this particular axis. And there you see, because things are coming closer to the neutral axis, therefore you have I2 which is much smaller, and that's the reason why EI2 is smaller. And therefore if EI2 reduces, you know that you basically have much larger kappa 2 than you would expect from a linear model. So that's the culprit is basically the in-plane warping. So you have W2 and W3, in particular W3. So there is a cross-sectional ovalization. It no longer is a circular cross-section. It's a oval type of cross-section. You can, because you can get closed form analytical solutions for your W2 and W3, you can actually get the geometric shape of the cross-section also as a vertically correct result for that. In the 1D analysis, what really is of significance is the fact that the bending stiffness EI2 effectively reduces, which means that the curvature is much more than is expected out of a linear model, which in turn means that the M2 versus kappa 2 is no longer a straight line, it takes a non-linear behavior. Is there any doubt on this Bezier effect so far? So same thing, let us look at for the trapeze effect. It's a non-linear extension twist coupling, as we said, in thin open cross-section beams, and also it's very predominant in strips as well. So for example, here we are plotting the elastic twist angle versus the axial force. Okay, so in the case of a helicopter rotor blade, this would be because of the centrifugal forces, because of the rotation of the blade primarily, and this would be the either in terms of the application of the control or because of the aerodynamic loading, and in addition you also have the pre-twist as well. But here we are only looking at the elastic twist over and above whatever initial twist you might have had in the structure. So now you're basically trying to pull this, and at the same time what is happening is its torsional stiffness is increasing. So it's very clear to see this is the trapeze which thing which a trapeze artist uses in a circus. It's a very simple thing. You have ropes with loops attached to the ceiling of the circus structure, and then you have a rod over here, and then you have these two things from which the artist basically hangs. Now you basically see if nothing is hanging, it's very easy to twist this. But if something is hanging out of it, it becomes much more difficult to twist it. In other words, when these ropes are under tension, it becomes more difficult to twist this, and depending upon how the weight distribution is, that torsional stiffness is going to change, and it is that effect which is basically appearing in engineering structures and what we call as the trapeze effect. So that's something which is predominant not only in strips but also thin-walled open cross sections, because in both these things the common factor, of course there are many differences between these, but the common factor is that their torsional stiffnesses are low. So because their initial torsional stiffness itself is very low, the twists can be fairly large. Even small torques can induce very large twists. So, and in a case where it is pre-twisted, for example, if this is a strip, the reason why this kind of a lighting is shown is to say that there is some kind of a pre-twist. There is no load applied, but even then the angle here and the angle here is different. In other words, your B2 and B3 are functions of x1 because B2 is always along the width, and the width direction changes, and along with it the thickness direction changes as well. So in such a case, for example, let's say I don't apply any torque, but I just try to pull it. You can very easily do this example in any pre-twisted strip that you have. You would see that there will be an untwisting of that. If there is already a twist there, you are just trying to pull it, then you will see that that twist will tend towards zero. So in other words, it will straighten out. So in other words, there is an extension twist coupling. You don't even need a composite for that. With just a pre-twisted isotropic material strip also, you can basically observe that. So there is this extension twist coupling has been observed over a very long period of time and taken advantage of also for entertainment as well as other purposes, engineering purposes as well. But what is becoming more apparent over time in the last 1 or 2 decades is the high level of non-linearity in this particular effect. In other words, that particular S12, the fact that it is there itself is an extension twist coupling. Whether it is a constant or not, even if it is a constant, there is an extension twist coupling. But what is more significant is that S12 is no longer a constant. It is a function either of your extension, strain, gamma 11, one way of looking at it, or in terms of kappa 1 itself, or again the pre-twist value small k1. So it's a function of all of those things. So now again, if S12 were a constant, then of course you would have had a straight line, and that's basically what this dotted line basically shows. And most people used to deal with trapeze effect for helicopter rotor blade analysis in particular using this particular model. But later, as we see, because of the warping that takes place, what exactly happens in terms of the warping, we'll go into the details later, but because of the in-plane warping in particular that happens, your S12 starts changing, and basically you see that this is the kind of effect that is basically observed. Again, there is a very significant difference here. You see that with the increase in axial force, of course here the axial force is tensile because it's a centrifugal force that we are primarily concerned with. It's not a compressive load. But in a tensile load, you see that what a linear theory predicts is a much larger twist compared to what the nonlinear theory or what in reality actually happens. So you see many of these experimental data are also there. So you see basically that it is lesser. In other words, it is actually a stiffening effect. In the brazier case, remember that it was a reduction in stiffness. It was becoming more flexible. The tube, as you started bending it, became more and more flexible and led to a moment in stability. Here, because I'm applying an axial load, the torsional stiffness is not reducing, but it is actually increasing because of the tensile load. It's becoming more and more difficult for me to twist. Whereas the pilot is trying to apply the control sticks, is trying to achieve a certain a twist angle. Because of the centrifugal force, it's becoming more difficult. Of course, you have fly-by-wire and things like that. You can boost the forces which are transmitted from the pilot to the blade. So that's not a big issue as such. But all of these things have to be taken into account in designing your control transmissions.
Sir, in the sense you said this, because there is no axial load in the wing, this trapeze effect is not much important. When you consider a moment, because of the lift, there is a moment in this. And when you consider a cross section and look at the moment, the stresses developed on that cross section, on the top half it's compression and on the bottom half it's tension.
Yeah.
Because of that there is an extension.
Exactly. Yeah.
So that then this becomes vital with pre-twisted.
Sure. If that is also twisting,
Pre-twisted.
if there is a torque or it is twisting, then it becomes very critical. You're right. Okay. So basically what it says is that if there is a non-zero value of your tensile load, or rather axial load, it could be tensile or compressive, basically theta 1 is not going to be 0 anymore. It is going to be affected by that because of the non-zero value of your S12. That is the first thing. But the more important thing is that this relationship between them is nonlinear. In other words, S12 is not a constant. The reason why it happens is, we saw in the case of the brazier effect, for example, it's the flattening, it's the ovalization of the cross section which was causing that, which is basically W2s and W3s. Now here what is happening is that there are local rotations which are taking place, and I described local rotation to you in the previous class. As opposed to the global rotation of a cross section, it is basically two adjacent points on the cross section having different values of warping, because of which there can be for example, 2 points adjacent to each other. This is x2 direction and therefore W2 direction. This is x3 direction. Now if there are 2 points here which are having different values of W3, one is moving more higher compared to the other, basically the line which is connecting them, which was originally horizontal, now basically becomes tilted. So that is that phenomena which we call as local rotation. And that is the culprit here. Unlike in the previous case where W2 and W3 by themselves were directly influencing that, in particular W3, large values of W3 were basically causing the I2 to reduce and therefore the stiffness, bending stiffness to reduce. Here what is happening is that there are local elements in the cross section which are turning. There is local rotation, and those local rotations are not small, and that is what is in turn causing this S12 to be a non-constant. Okay, now there are two situations. One is if there is a tensile load, that is F1 is greater than 0. In that case, as we can very clearly visualize, that is basically if somebody was hanging from this, the torsional stiffness is going to be larger. In other words, your GJ effective, if it's isotropic material, it is GJ itself, but in the case of a composite material, we can talk of an effective GJ, which is basically nothing but your S22 term over here, which relates the torque to the twist per unit length. So that Gj effectively increases, and that's basically the effect that you see if F1 is greater than 0. And also because of this increase in torsional stiffness, the frequencies, natural frequency associated with the torsional mode of rotating beams is much larger compared. It's a well-known fact that rotating beams will have much larger torsional natural frequencies compared to a non-rotating blade. The reason for that is basically this, that there is a torsional, there is a tensile load because of the centrifugal forces, and that is causing Gj to increase. If stiffness increases, the natural frequency increases because natural frequency increases with the stiffness. The next thing is, of course, the situation where F1 is negative. So if F1 is negative, then basically you can have what is known as torsional buckling. In most of the steady buckling, we are only aware of flexural buckling. That is basically when you have a